Hey, John here. Let's talk about the standard template library, what we call the STL. It's the acronym. What does it mean? Well, this is one of those few things that means literally what it says. It's nice to run across these once in a while. Standard. It means it's portable across all the different C++ compilers and operating systems. Template. It concerns itself with templates, okay? And the code that uses them. Library, it provides a collection of such templates and a bunch of functions that go along with them, all right? So that's what we're talking about here, all right? So let's go over to C++.com. Let's start out by looking at what we call the containers, okay? Now, in C++, if you click on like reference inside here, there's a heading that says containers and another one says other and some other stuff like input output. That'll be like how you write to C in and C out and things like that, right? So inside containers we have a various set of include files in here. These are the standard containers, all right? Now let's start with vector. And particularly the generic regular old vector thing here. Now this site has this giant menu. Let's see if we can scroll in, get a readable size font, and scroll over here. There we go. So what do we know about this thing? Look closely. This is a template class, right? It's not a class. It's a template that has a class in it, right? If you use this site, it drives me nuts. They hide it way over here. You see this thing over here? This is the name of the include file you need to include if you want to use this thing. All right. I would appreciate it if they just stuck it over here on the left, so that I didn't have to look over on the right. Anyway, it's just a personal thing. I'll call my congressman later. Anyway, so what is this thing? This is in the standard namespace, like string. We're all familiar with strings, right? This is a vector. Vector, you would expect it to be a template because it's in the template library. It's a template of stuff, right? And it is a template class, right, called vector. And if we scroll down here, blah, 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 blah. There's all sorts of stuff that it does, how its constructor works. It has a assignment operator and so on. It has various iterators. If you don't yet know what an iterator is, don't worry. Just be cognizant of a bunch of, these are basically member functions that return something called an iterator, right? For now, that's all we need to know. And look what he has. He has a begin, an end, R begin, R end, C begin, C end, and so on. Okay? Again, don't worry if you don't know what all this stuff means yet. What you do want to walk away with is the fact that these all exist. They have these names, and what they mean, if I call the begin method of a vector, class, it returns an iterator to the beginning of the vector, whatever that is. If I call end, it returns an iterator to the end of the vector. Again, whatever that means, okay? It has all these member functions. It has a bunch of other member functions that relate to the capacity of the vector. It has a thing called size, which tells you how many elements are in there. Max size, well, how many could I put in there? Okay, resize, it allows you to truncate the thing and shorten it if you want, or increase it and fill it with empty elements and stuff like that. How much space do you have reserved? So on. Again, we don't need to know everything about every one of these members right now because you can always come back to this website and look it up later when you need it. The point is, it has all these members that do things, and these are the names of those members. Down here we have element access. We're already familiar with these from the string class. You can use the square brackets to get each character one at a time out of a string. You can also use the @member function to do the same thing. Well, this also has the ability to just say, I can call front, a member function called front. Give me the first element of the vector. Give me the last one. And so on. There's a couple more in here. I can clear the whole thing out. Okay? There's a thing called pushback that I can call that would allow me to add a new element onto the end. Okay? This is something that you'll recognize and you'll see come back down the road here. Okay. Now let's go back to the the top menu in here. What else do we know about in here? Look what's not a container. Technically, the string class doesn't show up in here because it is not a container. It comes down here under other, all right? But let's take a look at it and compare it to the vector, all right? Here's your string class and all the doc that goes with it. Let's again zoom in and scroll over, and here's the, there we go. And of course, this time it doesn't tell us what we're supposed to include. Oh, it's because this is a higher level page. We have to click down here to see the actual string class. So let's start with the fact that this is not a template. So here's the thing we need to include if we want to use a string, right? We already know this one. We know this is a class. It's not a template. We don't say I want a string and then in square in these angle brackets put character in there. Okay. Now it turns out that this string class is implemented using a template, but that is completely beside the point. All right. You can implement the string object however you want. It is a class. It is not itself a template. That's why this is not in the standard template class. Now I'm making a kind of a academic point here. All right. Technically, it's not a standard container, and they go on to say this is similar to that of a standard container, which is a type of template, okay? But it isn't one because it's not a template. All right, let's move down here. Again, there's a lot of stuff in here, and we come down to its member functions. You know, we've used strings before. We've constructed them, and we've initialized them. We've assigned them values. Notice these look exactly the same as the the constructors for a vector, okay? Look at these iterators. Again, you don't have to care if you do or don't know what they are. This page is, again, we're now looking at the string page here, right? I don't even know because they're so identical, right? It has a begin, and R begin, R end, C begin, blah, 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 blah. Back to the vector page. Exactly the same thing, all right? So what is this? What's the takeaway so far? Well, if I have an instance of a vector, if I create a vector, that vector, if I want to, it has all these member functions, and I can call them. And they have the same semantics. In other words, they behave this same way. If I call the begin member function on a vector, all right, in this tab, we're looking at the vector class, it's going to give me an iterator that represents the beginning of the vector. If I call begin on a string, it'll return an iterator representing the beginning of the string. They have the same names. They have the same semantics, okay? Look at these capacity functions. Haven't we seen these before? They're not exactly the same, but they're very similar. We have a size. The string also has a length that the vector does not have, okay? Now, realize that C++ is like, I don't know, dang near 40 years old. When it was first, when the string class was first added to the language, it came along way before the standard template library was created. So the original string class had this length method in it. It may or may not have also had a size. Both of these, the point is, return the exact same value. It returns the number of characters in the string. I suspect, however, when they first created the string class, it had a length and some other things. It is a method, clear it out, delete all the characters, please. And the empty function is, is there anything in there? Hello, is there anybody home? That's the empty method, all right? When the standard template library came along, as we will see, all these so-called container templates have a size function in them. By adding the size function to the string, if that is indeed when this took place, it made this string start looking a lot like a vector. I mean, after all, isn't a string, even at the top of this page, we saw that it's implemented using some sort of a template that has characters in it. This thing, in a way, in basic, English, a string is a thing that contains a bunch of characters, right? So let's make it act a lot like a vector that is a thing that contains a lot of whatever you say. You could put characters in a vector. You could put integers, floats, doubles, and things like that. You can't do that with a string. You don't have characters in a string. But all these methods can do the same thing where it is appropriate. Okay, so let's look at some of the other ones. We got size, max size, resize, capacity, empty, reserve, shrink to fit, and so on. Resize, capacity, reserve, empty, shrink to fit. This one has a clear. All right. Now, why they just chose to put the clear? It turns out so does the vector, although it's hiding down here. Okay, so they actually have all the exact same functions to deal with the capacity of the vector as well as the string. And again, don't worry if you don't know what these all mean. Just accept the fact that they're all the same name and they all have the same semantics. Look at this. A string, as we already know, has a square brackets. We can say, I want the first character or the second one and so on, and treat it like an array. Or I can use the at member to say I want the element at, and then in parentheses give it the element number, like 5 or 6 or 7. I want those characters. I can have back and front, which gives me the very last character in the string, and front gives me the very first character in the string. Now notice this little C++11 in here. What that means in the way this website is set up, their convention is to let you know that these two member functions were not available prior to 2011, okay, on the string object. Let's look at the vector. On the vector, notice that front and back were always in there. So what do they do here? Well, in 2011, it was decided to make the string act more like the other container type classes. So you could still think of it, if you wanted to, the same way that you think about vectors in linked lists and decks and other such things, all right? So what else does it have? In the string, I could put a plus, and I can use that to append, more characters to the end, or I can have call a subroutine, a member function that just says append and put it on the end. And I can also call pushback as a member function, which will do the same thing, same kind of thing that append does. I want to be able to put, add characters to the end of the string. Okay, go back to the vector. What does he have down here? Well, he can assign things. He doesn't have the, he does actually have the square brackets up here. He has pushback. Add one new element to the end. Notice it says element because a vector could contain other things. It could be double precision floats. It could be integers. It could also be characters. A string can only have characters. So somebody added pushback to the string so that it can work it can work in the same manner that pushback does on a vector. I can poke one element at a time onto the end of the vector, just like I can characters on a string. Okay, so what do we got? We got insert, erase, swap, clear. Some of these become more vector-specific type functions down here. Again, if you look at the string down here, these are very much string-centric type of operations. These are not necessarily going to be available in a string, like a linked list or something. You're not going to want to convert all the elements in a vector or a linked list into a C equivalent string, right? You're not going to want to use a text substring extraction and things like that, all right? Or compare the contents of two strings. No, that really is very string specific stuff. But all the stuff up here is shared, all right? Now, some people might argue a string is a container. In a general sense it is, but technically it's not a member of the standard template library of containers, okay? But one of the benefits here is you already know how a string works, and every one of the member functions you already know how to use in a string other than these ones way down here. Okay, or rather, the ones that are in common with a vector, which is most of them, all right, give you a leg up on understanding how other containers work. And that's why we're kind of mishmashing strings in with vectors in this particular discussion, okay? So what's the takeaway so far? If you know how a string works and you know how to use any of the methods from here up on the web page, they all work the same way, for the most part, as all the same named methods on a vector. All right? So there's a huge benefit of having these things that are all consistent. All right. What's another benefit of having them all have the same semantics with all the same names? All right. Well, I have a little program I wrote here that has a template function in it. This is the entire reason that we have the standard template library of containers. Okay? Look what I can do now. I have a function called print'em. What does it print? Well, it takes a constant reference to a class of some type that I don't know yet. I wrote this function so that any class of any type can be passed in here, or more accurately, a reference to any class of any type can be passed into this function, provided that it has a size member function that returns the number of elements in that object, and it has an at member function that takes an integer that will return, oops, if I spell this correctly, a value from the container of the element at the given position I. All right? So what can I do now? This function can simply say create a variable called size equals the size of whatever it has been given. Then I can have a nice loop, iterate from 0 while less than size, add 1. I'm going to print them all out. What am I going to do? Well, this is in here so that I can put commas between them all without putting a comma in front of the very first one, right? So what is it going to do? For the most part, I'm going to go through all these elements, and I'm going to just say, give me the element at I, and I'm going to print it out. This is subtle. Okay? Let's make sure that we all understand exactly. This is the whole ball game right here. Okay? What does this thing do when it prints? When I say print this string onto cout, it has a string. It knows how to print a string. It's got, this is actually a string literal, which is a C string, which is an array of characters. The first character in the array is the one that's in the quotes right now. The next one, there's only one in there that's printable, a member of that string literal. The second byte in the array of characters that represents this string is a null character. So when cout is given an array of characters, what it's going to do is it's going to take the characters out of that array one at a time until it runs into the null, and it's going to print all those. And of course, it won't print the null, right? Then what is it going to do? It's going to call this member function here. But what's this thing actually going to return, and how in the world does cout deal with this? This is the essence of everything, okay? It is subtle, but this is the big benefit. C.at, if I pass this thing a reference to a string, it's going to return one character at a time. And when I give a character to cout over here, it knows how to print one character. It puts that character and prints it on the screen. But if I give it a vector of, I'm going to, down here in main, and we'll see in a second, I'm going to pass it a vector of integers. Now what's it going to do? C.at doesn't return a character. If I give this a vector of integers, it's going to return an integer. So this template function has to be, I would argue, I'd use the word instantiated twice. When the compiler runs, what's really happening here is it's going to go in here and go, I have a template function, so I'm not going to compile this. I'm going to just stash it away. And then later on, when I run into the main routine, and somebody says, print'em, and passes in a reference to a vector of integers, the compiler then goes up to this template class and goes, okay, great. I need to be able to compile up a bunch of code that knows how to accept a reference to a vector of integers. At that time, the compiler goes through and recompiles all this code. And the only thing that's unique and interesting and different in every time that it will do this compilation is that the return type, the value that comes out of this member function call, has a different type, which causes this to act differently. But otherwise, everything else is the same. All these c.size calls all return a size type, an integral type of size. Okay? And all the code would be exactly the same in every way, shape, or form except for this piece right here. And this is the beauty of all this, right? Why does this work? It only works because the vector and the string both have member functions called size and at that have the semantics that are necessary to be used in this context. All right? And because I created a template function, this is going to be recompiled over and over again for every single different type of thing that could ever be passed into this function. Now, if I call printem and I gave it, something else, this may not work very well, because if I give it an object that does not have a size member that returns an integral type, or it does not have an at member function that takes an integral type, then this can't compile. All right? So keep that in mind. But with all that now, let's look and see what's happening in main. I create a vector of integers called vi. I then created a string called s, and I'm going to print each of those two things out here. All right, so let's see, what do I do to fill in this vector? Well, I'm going to do a vector-specific initialization, because, how else am I going to put the values? I could assign them. There's many different ways to do it. I'm going to use that pushback function that we just saw in the C++.com website, okay? I'm going to say for I equals 10, less than 15, blah, blah, I'm going to count in the I. I'm going to put a 10, 11, 12, 13, and 14 in that array in that order. That's what this loop is going to do, right? This is going to create a string called S, whose contents are HELLO, exclamation point. Then I'm going to print both of those things out, okay? One of them is formally an STL container, and the other one has a lot of the same features and just enough to satisfy the needs of my template function. So if I compile this up, surprise, it compiled. Okay, let's run this. And it should do pretty much by now what you probably assumed it would do based on the detail that I just went over. So the first time it went through and printed out all the elements of this vector that are a bunch of integers. And of course I put quotes around them and neatly put commas in there and didn't put an extra one at the end and so on. And then when I called it with a string object, it went through and printed out each of the characters one at a time. So what's the takeaway here? The standard template library has a whole bunch of these template functions that match the needs of all of these container type templates. It's a family of things that all go together. All right? So you're going to see there's a whole lot of stuff. The begin and all this other, no so-called iterators. That has to do with basically if I wanted to print them out and I don't want to use an integer and count and so on, I can use these things called iterators and I can loop through all the elements that way. And there's some fancy things that you can do with these that are harder to do if you go through and you grab the count and you go one at a time and iterate with an index like this and use the at function and so on. My point is, if you have something like a linked list or some other data structure that's like a tree or something, asking for element number 5 may not be very efficient, okay, is my point. And we'll see more about that as we go. By creating this higher level of abstraction, is my point, then all types of containers can provide the most efficient manner to iterate across all of the values, all the contents, one at a time, okay, rather than just being, naive and going through them all one at a time and forcibly looking them all up by their index number, okay? Okay, so this is the entire point of the standard template library and of the container objects in particular, all right? So thanks for watching. I'll see you next time.